Forever to set the live streams. I freaking hate them. Oh well. Everybody ready to go?
Yes.
Is Seth coming?
He should be. He's so
Oh, that's awesome. All right. This is going to be the last lecture we have on AC systems. We're then going to go into digital systems after that. And my reasoning for that is because we've really beaten analog systems to death. There's a few other topics that you could talk about, such as filter design, but I don't want to. I'm ready to just go. Oh, hey, Seth. Congratulations, by the way. The lecture that you had last week on digital systems, it's kind of a preview way before it happens kind of thing. Yeah.
So this lecture is already for the second exam?
This lecture will be on the second exam, yeah. Yeah. All right. So we'll go ahead and get started. So we've been talking about AC systems for a while now. It's like the topic from hell that just won't go away. As a result of talking about AC systems, we've had to do a lot of discussions on phasors and then phasor math. Okay, we're going to do a quick example today, and then we're just going to put this thing to rest. I will note here that all of our conversations, again, about AC systems, this has only been for steady state systems. Which means that none of these have that transient portion. So basically, what that infers is that all of these systems, we are basically only solving for the homogeneous solution. Nope. Particular solution. My bad. Okay. All right. So we'll do one last example. And this one will be a little bit of a doozy. So this will be R1, R2, L, C. This will be VS. We'll go ahead and assign some values. We'll say that VS is equal to 30, and then because it's a phasor here, we'll set it at 0 degrees. We'll say that R1 is equal to, we'll set it at 500. And then once again, well, that's 500 ohms. So I'll just write ohms. R2 is equal to, we'll put this at 200 ohms. We have L, we'll put this at 8 henries. We have C, and we'll put this at 10 microfarads. And then we've got omega, which we'll go ahead and put at 100 with units of 1/2. Okay. So the way that we solved the last problem was we actually built this thing, KVL, KCL, wrote out all the equations, came up with a system equation, solved the system equation. There is an easier way of doing that, and it does involve some phasor math. So here, the question is, how do we find VL? Okay. So let's do a throwback to a long ago time when all of us were younger, the world was brighter, and no one had yet taken a circuits exam. Okay. When it comes to finding VL, what we can do is overall we know that the equations for every component, so V component is equal to I component times the complex impedance of that component. Okay, we know that to be true for everything. So what we can do is we can go ahead and collapse all of this into one single complex impedance. And by doing that, we can then apply this equation, find out the source, and then step back through the system to identify what we're dealing with. Okay? We did that when we dealt with equivalent resistances. So we're going to solve this the exact same way as we did equivalent resistances. By the way, because we're using this format here, every single method of solving a resistance-based system, which could be the mesh current analysis or the node voltage analysis, either of those, the equivalent resistances, every one of those still applies. You still have the current division principle and the voltage division principle. Those also apply here, although in a little bit more of an abstract sense. But we're basically just dealing with resistance-only circuits one last time. Okay? That's all that this is. So, the first thing I'm going to do is I'm going to collapse either components in series or components in parallel. Okay? Doesn't matter which components they are, we can collapse them all. So the question is, which ones do we combine first? This one? With what? L? Why would we do that? It's called vision, my friend. So if we just combine these two, then we can combine all three of them. So for our first iteration of an equivalent system, we're going to bring this. So this will be R1. So come over here. I'm just going to drop a box because it's both a resistance and an inductance. And I'm going to call that ZEQ1. And then it's going to come over here, become a capacitor, and go back here. Okay? So here, we know that since we're combining these in parallel, what we have is that 1 over ZEQ is equal to 1 over Z1 plus 1 over Z2, because this is a parallel system. So, because this is a parallel system, we're going to go ahead and add them like this. All right? And by the way, this is 1 angle 0 degrees, just because that's what it is. But I won't write that up there. So what we have, when we go to write this all out, 1 over ZEQ 1 is equal to 1 over Z1. What is the complex impedance of R2? What?
200 ohms.
It's 200 ohms. What's the angle?
0.
Okay. What is the complex impedance of the inductor? What's the equation for it? So it'll be what?
WL angle 90 degrees.
Okay, so omega times L. So this will be 100 times 8 angle positive or negative?
Positive.
Positive 90 degrees. Okay. Okay, so all we're doing is we're just combining those like that. So here we have 200 angle 0 degrees, we have 800 angle positive 90 degrees, and we're just combining them. Okay, so 1 over ZEQ1 is equal to 1 over 200, this would be 0.005 at an angle of 0 degrees. And here, this ends up being plus 1 over 800. 1 over 800 is that divided by 4. So that's 0.00125 and an angle of, and here it is at positive 90 degrees. I was wrong. That's not 1 at an angle of 0 degrees. That's just 1. So it's just 1 divided by that sine curve. No, that would make it negative, no matter what. My bad. So it's because it's a 1 over, it becomes a negative. So now what we do is we break this into components. Okay, 0.005 at an angle of 0 degrees becomes 1 over ZEQ1 is equal to 0.005. Whoa, that's too many zeros. Cosine 0 degrees plus 0.005 sine 0 degrees plus 0.00125 cosine negative 90 degrees plus I forgot to write, nope, we're using J. Because it was a 1 over. Times J times 0.00125 sine negative 90 degrees. Okay. All right. Now we know that sine of 0 degrees, that goes away. And cosine of 90 degrees, that one also goes away. So what we're left with is 1 over ZEQ1 is equal to 0.005 minus 0.00125 J. Okay? So then all we do is we find what that is. What?
Why just J? Why don't we have I?
In electrical engineering, oftentimes they use J instead of I because I stands for current most of the time.
Oh, okay.
So, yeah. You could write I. There's no problem with that. It's just...
Oh, like I for the first part. 0.005I. And then minus 0.00125.
Oh, why do these go away?
No, like you just have a singular component instead of an I and J direction. You just have unnamed direction and J direction.
That's because this one's real and this one's imaginary.
Imaginary.
The real one doesn't need explanation. It's actually the real and imaginary axes. That's the definition. You could write an R on there. If you really, really wanted to, you could write the real symbol on there. I'm not that person though. But technically that is the coordinate system, is it's the real and then the imaginary. All right, so we'll take this and we'll find out what the complex impedance is. 1 over ZEQ 1 is equal to 0.005 squared plus 125 squared. Squared answer 0.00515 at an angle of negative 14 degrees. Okay, so then what we do is we have to invert this to make it ZEQ1. So this becomes 1 divided by 515. So ZEQ1 is equal to 194.17 at an angle of 14.03 degrees.
How do you get 515?
This one? Well, this is the magnitude of this squared plus this squared, the square root of that. Any other questions? This isn't easy math. We left easy math a month ago. No, that's a good thing. Like it's fine that this is a little confusing because this is friggin' hard and phasers friggin' suck. All right, so now we can replace this with this component here. So we'll just do that. Okay, and then we'll go to our second equivalent circuit, which is VS ZEQ2, and that's it. Okay, so we're combining all of these in series. So here, the equation for combining in series is the same as resistance. ZEQ is equal to Z1 plus Z2 plus Z3. So here, ZEQ2 is equal to complex impedance 1. What is the impedance of R1? Which one? What? So it'd be 500 angle 0. Okay, what is the complex impedance of, well, we've already got ZEQ 1. That's this thing. 194.17 angle 14.03. And then the last one is, what is the complex impedance of C?
1 over omega c.
So 1 over 100 times, and that is 10 times 10 to the negative 6th for C. And then that is at an angle of negative 90 degrees?
Yeah.
Okay. So this right here becomes 100 times 10 to the negative 6th. This becomes 1,000. So all right, so we have ZEQ2 is equal to, we're going to go ahead and break up each of these components. I'm going to write 3 different lines, and then we'll add all 3 of those lines together. So this will be 500 cosine 0 degrees plus j times 500 sine 0 degrees. And then you have 194.17 cosine 14.03 degrees plus j times 194.17 sine 14.03 degrees. And then our next line, which is 1000 cosine negative 90 degrees plus j times 1000 sine negative 90 degrees. Okay, so we'll go ahead and add Well, we know this becomes 0. We know this becomes 0, so that's nice. So we're only adding these two and then these two components together. So I could write that out, or I could just do it on my calculator and then tell you that that's the truth, and you can just believe me blindly. So this becomes 688.38 plus 1047.07 J. Okay? But once again, you just blindly believe me. The world will be right. Listen to everything I tell you. I disagree with you.
Wait, never mind.
Yeah, because it's...
Yeah, I didn't use the other 10. So.
Yeah. Yeah, otherwise you would have been right. Okay. Look at you checking my math. I tell you to blindly believe me, but seriously, that's what I want. I make math mistakes. I'm friggin' doing everything on my phone calculator. I don't know, I've already done that for your class once. That was last class. Good times. All right, so let's figure out what the magnitude of this vector is. It's just 6. So I get 689, that's not right. That's not right. Yep, that's what I got. 1253.09 at an angle of 1047. 107. Wait, is this a minus or a plus? This should be a minus, shouldn't it? Dang it, it is a minus. That's my bad. This number's wrong. This sign of negative 90 degrees becomes a negative number.
Wait, I thought it was because it was underneath the long Chinese.
This one, because we're adding in series, it's not underneath a 1. The coefficient is under a 1, but that's what turns it into 1,000. So it's basically 1,000 at an angle of negative 90 degrees. So this one actually becomes 952.93 J. Which that does change things a little bit. Ah. Bum bum bum. Stop doing that. What? It's not 10,000. Your calculator's a liar. Because this is 100 times 10 times 10 to the negative 6. Yeah. Yeah, no, that would be 10,000. Okay, so this actually ends up being 1175.56 at an angle of well, it's because this number ended up decreasing by almost 100. At an angle of negative 54.16 degrees. Okay, so that is the complex impedance ZEQ2. All right, now what do we do next? We found the complex impedance.
Stop.
We stop.
Submit.
We just type in the answer because that's it. No.
Maybe what if the question was final complex?
Yeah, but except for the question is, how do we find VL?
I'm pretty sure there's like a website that can do that.
I mean, probably, and if there isn't, you could code one, and it wouldn't be that hard.
What's your answer? In the box where it says how do we find VL, you put Google.
There it is. Found it. So what do we do now? In equivalent resistance circuits, what did we do next? You step it, you simplify the circuit down into one resistor. Then what do you do? Yes, there's a D, yeah. You find the current. How do we find the current? We use this handy-dandy equation, which just looks like Ohm's law, but just a complex form of Ohm's law. We can use this to find I that is flowing out of the source, IS. Okay? So here, we can say, even at the very edge of, I don't even think anybody could read the text on this video, if I'm honest. Yeah. It's crazy. Even on your phone?
Yeah.
That's so small. All right, so we can take this complex impedance, we can find IS. So here we know that VS is equal to IS times ZEQ2. So that means IS is equal to VS divided by ZEQ2. Am I doing that right? Yes, I put it on the top this time. Yes. So here we know that VS is equal to 30 angle 0. So 30 angle 0, 0 degrees, divided by 1175.56 angle negative 54.16 degrees. So we just do some quick maths. So this becomes IS is equal to 0.02552 at an angle of this minus this, so that becomes a positive 54.16 degrees. Heckin' yeah. All right. So now that we've found IS, what do we do next?
Now we're breaking down to VS is equal to VR plus DC plus VL.
We step it back to here, and then we break it down. Wiki wiki. I used to be a DJ, but only for my mom. Yeah, she said it was great. She was like, "Boy, son, you really break it down well. You keep it down, though." I was in high school in 2003 to 2007. Yeah, it was good times.
I was in the kindergarten.
Yeah. Good times. That's back when all of you were rolling in the crib. Yeah, you guys probably would have thought it was great too. That guy's awesome! Yes! Yeah, rolling in the crib. Yeah. No, I never did any beatboxing when I was young because I recognized I had limitations.
You got a comment.
Wait, what?
Oh, let's go.
Milana Sidral.
Oh, sweet. All right. Hold on.
Something in fucking Russian.
Let's go. Another profile.
It actually has a profile picture though of an actual person.
So long. That's what it
Oh,
says.
yeah.
Do you have an actual viewer?
That's hilarious. Yep, good times.
No, you've been gone for so long.
No.
Silly.
This is, well, yes. It's a phishing attempt, though.
Yeah.
So, all right. We've done this. We're going to go ahead and step back and find out what the voltage is across ZEQ1. Why are we doing that? Why would we find the voltage on ZEQ1?
When we break it back out into parallel,
Yeah, that's the answer. Yeah. Well done, Zane. So we're going to find VZEQ1. So VZEQ1 is equal to IZEQ1 times ZEQ1. What is IZEQ1?
it's the system.
It's the current that goes through the entire system. It's what we found right here. Here, we know IS. Are you trying to pretend you're 26 again?
Nope.
He said something else that I have no clue what he said.
Now that you heard this professor.
Yeah, please no.
Oh, we got a hell of a
Oh.
No way.
You're cheating on Olga.
Not Olga.
I'm more interested in what Donkin said.
I showed your sister a channel.
Oh,
Wait, what?
she showed her sister his channel.
Donkin, you gotta ask.
This one.
Donkin, you gotta ask if she's 26. Come on, flaunt that money. Okay, so this ends up equaling 0.02552 angle 54.16 times ZEQ1, which is 194.17 at an angle of 14.03 degrees. Okay, so when we multiply, again, these two pieces multiply, these two pieces add. So 194.17 times 0.02552. This is equal to 4.955 at an angle of 68.19 degrees. And that's our answer, right there. And that's in volts.
Did you just add the angle to them?
Yeah.
You also got some Spanish speaking friends on the line.
Oh, no way. Those are my homies.
Sam.
What's Sam say?
Oh, that's great. All right. Any questions on how we got this? Seeing no questions, I'm going to tell you anyways. So, what we started with is we have our system, and then our goal was we were going to use equivalent impedances, the principle, to step down in the system and then step back. Okay? So we're doing this exactly the same way we did equivalent resistances. First step, we combined in parallel. We then found ZEQ1. Through this process, we had to use this fun formula. We got to here. We then stepped down again to get ZEQ2. We then found ZEQ2. Then our next step was, now that we have our complex impedance, we needed to use this to determine how much current was coming out of the source. So we plugged that into this equation. We get IS is equal to this value. We then step backward. We know how much current is coming out of the source, and because, if you use KCL in this system, and since all of these components are in series, they all have the same current. So we already know what that current is because that's what we calculated. That's the voltage here. Once we calculate the voltage, we know all components that are in parallel have the same voltage. So all components in series have the same current. All components in parallel have the same voltage. Since we solved for the voltage here, that is the voltage here. We could further solve for what the current is in L, but I don't like AC systems and I want to be done. All right, so let's go ahead and get back here, 9:05, and we'll keep going on. We're going to introduce some topics in digital circuits.
What did Duncan say?
What, Donkin?
What did Duncan say? Hey, you got a lot of views today. 3 live views,
Oh man,
4 different chatters.
I'm going to start monetizing this. Oh yes!
What